Yeah, so good evening, and we'll start today's class. Uh, till last class, we finished the discussion on the content that was actually taught in the class. So now this is like a revision class, and we'll discuss for this uh, whatever we studied in our previous 12 classes, because it was uh, you know quite long class, 12 weeks, so around 3 months, roughly speaking. So yeah, that's the agenda today. We'll take some problems because from this casting, forming, even welding also we took some problems, but I'll just recap it for you. For if some of you are preparing for some exams or something like that. Uh, and one thing that this class primarily focused on casting, forming, and welding, but that's not the end of it. Mm, there are many other things also in production processes. Uh, for example, you have something called as uh, tool geometry and metal cutting. That topic is also quite involved because there are a lot of angles that you need to be considering for making a tool which is used for metal cutting. So that is also important for competitive exams like GATE, etc. Apart from that, there is new topic uh, recently started gaining more attention, which is called as non-renewable production processes. Sorry, non-conventional, not renewable. Sorry. It's called as conventional production, non-conventional production processes. So there are different type of processes in that, and you know, uh, for example, like CNC and all those things uh, come under that category. So if you are preparing for competitive exams, those things are also important. For like we did not discuss that in this class, but that doesn't mean it's not there. It is there. You are supposed to know some things if you are preparing for some exams, and you could find that information. Maybe nowadays online resources are also there, but any standard book, if you go and study, you'll find those. Apart from that, there is something called as very important process called as drilling, which is also not discussed here, but comes under production processes. Because most of the times, you must have seen drilling because it's a quite universal process. Then there is something called as honing, tapping, uh, all those things are there. So rimming, milling, so all these also come under the category of production processes. Even though we did not study, I'm just giving you the names so that you'll know the vastness of this subject. And you know this is not the end of it. Maybe this is like limited course syllabus for this course, but in general, production processes, it's a quite huge topic, and that's why it's challenging to study them for competitive exams because they can ask anything from any topic. You are supposed to know the basics at least. Grinding process is there. uh, yeah, and then there are non-conventional processes. I'll just uh, tell you uh, these because the metal cutting, etc., they are basically using the shearing force to cut the metal. Then there are some methodologies which use erosion of your bulk material to remove that material, so, such as water jet machining, ultrasonic machining, abrasive jet machining, you know, so those kind of things are there. Then sometimes we use electrochemical dissolution processes to do the removal of removal of material from the desired or the initial product to get the desired product, something called as electrochemical machining. Uh, then sometimes we just use corrosion also, not that widely followed because corrosion once it starts, it's very difficult to control. But in some cases, that kind of things are also there. But then there are like important techniques which use electric spark, so EDM, electric discharge machining, EBM, LBM. We have seen plasma arc welding. We have seen, EBM is electron beam, LBM is laser beam, etc. Last class only we have seen those. So it's a wide variety of processes. Okay. And nowadays there is this robotics also. I mean, not like a strictly mechanical subject, but in in production processes, many a times, uh, the CNC machine, etc. We use commands, so you should know. Then there is the topic of metrology, in which you study the measurement principles like accuracy, repeatability, all those things, precision, and then there are some numericals because this fit, there are three types of fits: clearance, interference, and transition fit. So in GATE exam, many times they ask questions on that. Maybe that will be taught in separate syllabus, but it is also under kind of subtopic under production processes. Okay, so you should know all these things, jigs and fittings, all those things are there. Okay, so it's quite a challenging subject, to be honest. And then finally, there is this topic of surface roughness measurement, very difficult, important but difficult. Okay, so what I'm trying to say here is it's not only these three processes like casting, forming, and welding. They are the uh, conventional one and widely studied, widely used. So maybe that's why we are studying them in this syllabus. And to cover all the production processes, maybe 12 weeks are not enough. So that is also constraint one sometimes. So, but nonetheless, you should know that production processes is not only these three. There are a lot of production processes that we, uh, as a mechanical engineer or practitioner of mechanical engineering subject, you are supposed to know. Okay, so if you are taught in your colleges or wherever you have studied, uh, you can just revise them. If not, because I've seen many places they are not taught also properly, so you should refer to standard books. NPTEL lectures are also there. Apart from this course, there will be another courses where you'll get the information about those. Okay. So with that background, let's start the revision. Okay. So as I said, we started with the this metal. Sorry, we started with casting. Okay. So what I'll do, I'll just revise all those things for you, important topics. Maybe on the way we can take some problems also. Okay. So casting, we spent about 4 classes on that. So let's talk about casting. And there actually I think we skipped one topic which was about different type of casting processes. I thought of covering it in I think third or fourth class, but then something else came up because after pattern materials allowances, uh, you know types of patterns, then you have covers, chaplets, that kind of thing, molding sand, you know elements of gating, all those things are there. But let me just see different types of casting processes. Did we? Yeah, this riser is there. Yeah, this casting processes we should actually talk about. Okay, so yeah, maybe we'll discuss that part because I think that was the part which we did not discuss because before casting defects we should know what type of different casting methods are there. Okay, so okay, so what I'll do, I'll just briefly revise this casting topic for you, whatever we studied earlier, and then I'll talk about this casting, different types of casting processes, how do you classify those things, etc. Okay, and then we'll see. Okay, so I thought we'll take that because we missed it in our casting discussion. So casting, it's a single step kind of a manufacturing process. I mean, there is a finishing etc. required towards the end just to conform to the final dimensions, but typically speaking, casting does not involve a lot of number of steps. That's why many a times if you design your mold and material and pouring everything perfectly or properly, you may not need to have some processing or something like that apart from finishing. Okay, so that's why in many places they call it a single step manufacturing process. It's a primary process, basic manufacturing process. There are some processes which are called as secondary or derived, such as, let's say, forming or other kind of things where you use products given by casting to do some later on things. Okay, what are the advantages of casting? Sometimes these are also given in the options of MCQ questions. You can manufacture, you can do casting for wide range of complex shapes, wide range of materials, sizes also. You can make small size components as well as very huge components using casting techniques. For that matter, for huge or large components, casting is the only feasible technique to make them. Okay, so it's not a very trivial kind of technique nowadays also, even in the age of robotics or anything else. Uh, if you want to make bigger components, casting is the only way. Okay. Then you can use casting for mass production, so sometimes it is cost effective. You don't need skilled labor. That is also one of the you know very good advantage of casting, because if you do welding or some other kind of processes like bending, metal forming, bending kind of things, or even metal cutting, sometimes it comes down to the operator skill, labor skill. But casting, the advantage is you can rely on less skilled labors also. Okay, you don't need very expensive tools also. Mostly it is moldings and patterns which are quite cheap. Okay, so first thing that you should revise is about advantages of castings, advantages as well as limitations. Okay, and you can do this for all three. So like not only for casting, you can do this exercise for formings, metal forming processes and welding processes, because you should know why you are studying some process and what are its advantages, what are its disadvantages, etc. Then we briefly talk about nucleation. In practice, mostly it's heterogeneous nucleation. Homogeneous nucleation is a more of idealized concept. So you can revise that, but as far as the practical things are considered, it's always heterogeneous. This thing, nucleation, because in casting we typically talk about liquid to metal cooling transition phase, so phase transition. So and if you have pure metal which is being casted, it will have a uniform or constant melting point or freezing point. But if it's alloy, it will have a range of melting points. It will be like a mushy zone formation kind of mechanism takes place there, and then you'll have gradient in that mushy zone depending on the solubility of various phases. Okay, so that is there. Then very important is this Chauvinov's rule. Okay, and most of the GATE exam problems are from this rule only. Okay, I mean not all, but many a times they ask this. So here you have solidification time is proportional to the volume by surface area of the casting whole square. Okay, so sometimes you'll see something like T is equal to V by A whole square. Okay, so this is very important because they can frame many questions on this, and we solved also some questions. So in which you have cylindrical geometry and cylindrical casting geometry, and then you have a cuboidal casting geometry, and you assume that they are purely metal and their temperature is also same at the start. So which casting will solidify faster, or what will be the ratio of the solidification time, all those things. So basically you have to use this Chauvinov's rule, Chauvinov's. Okay, quite a difficult name to pronounce, but leave the name, take the game. So that T proportional to the V by A whole square is the main thing you should remember. Okay, so we solved different problems on this, and be careful, okay, because what happens, they sometimes try to trick, because people sometimes, if they remember this formula, they become overconfident, and in exam they don't pay attention to what is actually given. So what examiners do, sometimes sneaky things they do, what they'll say, it's a cylindrical casting, but only top surface is exposed to the atmosphere. So basically they are hinting at, you know, hinting sometimes that bottom surface does not participate in the solidification process or something like that. Okay, they may say that bottom surface is very well insulated, something like that. So you have to be careful. Okay? So because volume is fine, volume anyway you can calculate based on the dimensions, but this surface area, it should be only that surface area which participates in the heat transfer process for the freezing. Okay, so keep that in mind, because I have seen sometimes they try to trick in those questions. Okay, then cube, sphere, cylinder, these kind of geometries are there. You are supposed to remember the formula for volume of all these three, and surface area. Surface area of sphere is 4 pi r square, volume is 4 by 3 pi r cube. Okay, and yeah, that is, as far as numericals are considered, that is one of the important ones. Then, you know, we studied something about solidification of alloys and different type of grain structures that followed, that are observed in alloys, because in pure metals, as I said, the melting point is constant, so you have basically equiaxed grains toward the container boundary, and towards the core of the casting you'll have large. But in case of alloys, you have this dendritic structure formations in the bulk of the metal alloy casting. On the boundary, it will be equiaxed grains only, but in the bulk, you'll have dendritic, and then there will be some equiaxed dendritic grains in the center. Okay, so you should remember the difference, because sometimes they may give questions like, you know, dendritic grain growth is a characteristic of, then there will be 4 options. So you have to tick metal alloys, okay, or typically alloys, because alloys usually we talk about metals only. Okay, because, you know, it is important for exam also, but other thing is, you know, practically also you should know, because when you do casting, uh, as I said, it's mostly a single step process. So whatever you get at the end of the casting, that's your final product. You know, so all the material properties, characteristics are decided. So that's why you should know what kind of grain structure you'll have. Then you'll, you know, have some idea about the strength of that casting, under what kind of loading it should show some strength, or it should show weakness. All those things you can guess. Okay, because everything is affected by grain boundaries and grains, type of grains, like grain characteristics and grain boundary interactions. You know, because in this cold working, etc., we discussed about uh, grain boundary interactions, right? So everything, if you go to the root cause analysis kind of technique, you'll realize that everything boils down to the uh, grain structure and grain boundaries interaction. Okay, so just a second. Yeah, so this is about uh, solidification that we studied. There is something called as central line feeding resistance, CFR. Okay, so which means the time required. It's a ratio of time required to solidify at the center to the total solidification time. Okay, so, you know, uh, it should not be very high, or it should not be very low. So there is a optimum thing which is, therefore the CFR becomes important. Okay, it will be always less than 1 because denominator is uh, total time, so it will be always less than 1, but you need to have some idea about that also. So sometimes in casting terminologies you'll see this center line feeding resistance. Okay, I'm just noting down important things that you should revise. Okay, because I think some of you will be giving exam also for this course, so it will be better for you. Then fluidity, because in casting fluidity is very important. Not so in other techniques, maybe in welding also, but in casting it's very important because mostly that is what determines the amount of material or the location of the solidification front, etc. All those things. Okay, so usually this spiral fluidity test is done. Nowadays there are many other tests also, but conventionally this spiral fluidity test is there, which is mostly affected by the starting temperature or pouring temperature. That is the most important factor for that fluidity test. Okay, there are other factors which affect the fluidity of your liquid metal, but temperature, pouring temperature is the most significant one. Okay, and then we discussed about different type of pattern materials. Okay, so usually you have two type of pattern materials. Okay, wood, which is most commonly used because of various advantages, and then you'll have some metals. Okay, so we had discussed their advantages, disadvantages, everything. Wood, the most lucrative advantage is it's cheap and easily available. You can have different kinds of woods. uh, Usually no issues of corrosion if humidity is not very high. Okay, lightweight, because that is also one safety hazard. Metal patterns are quite heavy because of higher densities. Machining of wood is also not that difficult. You can just use a normal axe or something like that. But for metal cutting and all, you may need sophisticated tools. Okay, so these are some pros and cons. But the advantage of metals is that they don't have this volume shrinkage and bulking kind of issues depending on the moisture content in the surroundings. So for mass productions, where your cost is secondary to the I mean, not secondary, but you want the accuracy or precision over the cost. In those cases, metals are preferred. Then different types of patterns. Okay, so you should revise all these things. I'm just giving you the keywords. Okay, so different types of patterns. uh, Single piece pattern, or solid piece pattern, simple piece pattern, all are same name. So something called as single piece pattern. Then there is something called as split piece pattern. So in that case, you have two separate what is called cope and drag, and you use dowel pins to make sure they are correctly aligned. Then you have loose piece patterns. Sometimes you have extrusions, um, and to take care of that, you use loose piece patterns. Gated patterns. Okay, so maybe I'll just put. Okay, so we have already discussed these, but you should always revise and remember the pros and cons and what are the applications, all those things. Okay, then there is something called as match plate pattern. Then you have sweep pattern. Okay, sweep is used for axisymmetric kind of castings. It cannot be used for other things. Then you have follow board pattern, used for hollow or thin structures, structurally weak kind of patterns or castings. And then you have skeleton. So this is useful in the big kind of castings. Okay, because otherwise you'll need a lot of molding sand, which is not a good idea. Okay, So this was about types of patterns. Then we discussed something called as pattern allowances. Okay. So these are also important. Many times GATE exam questions are asked on this. There were like few allowances. First is called as shrinkage. One second. Shrinkage or contraction allowance. Okay. So basically, when your liquid solidifies, its volume shrinks in most of the cases. So you consider that before you make the mold, you basically make a larger mold so that when it solidifies, you'll have shrinking, and that will be equal to your desired final casting. This thing, you know, final casting dimensions. Okay, so here one catch is there. You should always remember. See, shrinkage contraction allowance is called as positive allowance because you make mold bigger than the casting, final casting. So it's in that respect it is called as positive allowance. But you should always remember one key exception to this, because previous gate year exams they have given question for this only, except for gray cast iron it is negative. So basically because of this flaky structure of carbon in gray cast iron, instead of shrinking, overall shrinking of volume during solidification, you will get overall expansion of volume, or this volume expansion. Okay, so just keep that in mind because in gate exams they have asked this 2 times. So apart from that, there is something called as draft or taper allowance. Okay, so this is because when you have vertical surfaces, usually you can't just pick, pull it out from the uh, parting molding sand after ramming. So you need some you just shake it. So therefore it is called as draft or taper allowance also, and that will make your casting slightly bigger, but then you finally you do some finishing and you cut it off. Okay, so this is also positive allowance. Then you have machining allowance. So as the name suggests, sometimes just to conform to the final dimensions, required dimensions, you do slight machining. So that is also machining allowance because of first dimensions and then surface finish also. You need like a smooth surface finish, etc. Okay. So then there is something called as shaking or wrapping allowance. Okay. So this makes your castings uh, you know like you make mold smaller so that uh, when you shake it, it will slightly be bigger and your final casting will be bigger. So the point that I'm trying to make here is uh, uh, okay. So it is the only allowance which is negative. Again, one MCQ question. Only negative allowance in pattern allowances is the shaking allowance. Okay, this is compulsory. This taper or draft is optional because sometimes students think these are all same only, these two. But that is the difference. For vertical surfaces, shaking allowance is always compulsory. Taper or draft, it's up to you. If you want to give, give. Otherwise, it's fine. And then there is final allowance, which is called as distortion or camber allowance. Okay, so it's neither positive or negative. It's just you know, when you know that it is going to shrink, so instead of getting vertical walls, you'll get some bend walls. So you give that bend initially in the pattern or mold only. Okay, so that is what these allowances are. We are supposed to go and revise these. Then there were discussion on this molding material, desired properties of molding sand, etc., etc. Then for this molding sand, there is something called as grain fineness number, GFN. So higher it is, the finer the sand is. Okay, the lower it is, the coarser the sand is. Okay, so you should remember that. Then there is something called as permeability number. Defined for the molding sand, PN. It is nothing but VH by EA into T. Okay. Sometimes this you should remember they are followed some units. Okay, so you have to pass 2000 centimeter cube of air through the sand at certain constant pressure P, air pressure. Take it as gauge pressure, okay, not the absolute pressure. And why? Because this permeability number is calculated in the field. So there usually you just take the reading whatever shown on the gauge. Okay. Area, I think it is 2 by 2, so or 5 by 5, something like that. I mean, this is standard uh, size, so you should have this much area and height of your this 2 by 2 inch, I think. Yeah, something like that. And then time in minutes. So for how long the air was passed at certain pressure P through this uh, sand in minutes. Okay, because this is also sometimes directly asked. So if you put these constants, you should get some 500 by PT. Okay, but like that you should remember. Just a second about this permeability number. Yeah, the pressure usually is in gram per centimeter square. Okay, so like that. So if you put those values, you should get some number. Usually this number is between 60 to 90. Okay, so sometimes when you solve, you should also know what is the correct range, because you might have made some calculation mistake or some mathematical mistake, so you should know. Okay. It should be around 60 to 120. Then there was discussion on core and chaplets. So core basically is provided for hollow casting, so that the hollow part is been replaced by core during casting. So the core should be having enough strength because it will experiences thermal stresses, buoyancy forces, okay, variable things during casting solidification. Okay, so to make sure that core doesn't shifts or doesn't offset from its desired position, sometimes these core prints are used. Okay, so they make sure that your core remains in the desired location, and these core prints usually get dissolved in this liquid metal only, so they are usually made up of same material as the casting material. And then you have something called as chaplets, who chaplets are the components which support the core. Okay, so all those things are there. Then in the third class of casting, we basically started on gating system. Okay, so important as far as uh, numericals etc. are considered, because there are different cases here. So gating system or gating design. So you know you should go back and check what all the important uh, you know important components of gating system are. First, we start with the pouring basin, and you usually use a strainer there to remove any impurities at the top only. Then the liquid metal flows through sprue, to the sprue base well, where you basically put some splash core or something like that to reduce the splashing losses. Then you have a horizontal runner typically with the skim bob. Skim bob is a part of the runner where you remove lighter as well as heavier impurities before entering into the mold. And then you have mold cavity, and to ensure that it is completely filled, and to give the way to the air to remove from the casting or mold as liquid metal is getting poured into it, we provide risers. Okay, so when you start pouring basin from one end and you stop when you see the riser level or riser is completely filled. Okay, so that is how this gating system works. Okay, so proper gating system will give you good casting yields. Casting yields is basically nothing but how much volume of mold cavity you are filling divided by total volume including cavity and the gating system. Okay. So in these cases there are certain considerations that you should remember, because there are some problems. So basically some problems are asked from this sprue design. Okay. So usually first thing is this sprue. Yeah, ideally it should have, ideally it should be parabolic in shape, but it's difficult to construct parabolic shape in practice. So practically mostly it is tapered cylinder. Okay, so practically it is a tapered cylinder because it's easier to make that shape. Okay, and why do we have this parabolic in shape? To avoid something called as air aspiration. Okay, so we have seen what is air aspiration, because when liquid metal is hot, it has uh, higher solubility for atmospheric gases, and we don't want that, because in atmospheric gases there is something called as oxygen. So oxide formations will take place, and that will affect your casting quality, casting yield, all those things. So we want to make sure that air aspiration doesn't happen during casting or pouring. So therefore there is one derivation that we did. Basically, you can apply mass conservation at the top and bottom. So you have something like this kind of a shape, right? So you have 1, 2, and 3 points. Okay, so this is your sprue, and then basically you have this different heights. So this will be your total sprue height, HT. This will be your some basin height, HC. This is your sprue height, HS. So we had done this derivation that V3 will be under root 2G HT. Okay, V2 will be under root 2G HC. That A3V3 is equal to A2V2. So sometimes they ask these kind of questions, and usually you eliminate this HC because usually they give you HT and HC. So you can just put this as equal to HT minus HS. Okay, so all those kind of things we have discussed and solved some problems also on those kind of questions. Okay. So this was about sprue. So you should remember that ideally it should be parabolic, but it's not possible practically to do that. So it should be tapered cylinder practically. It is. Then you have runner. Okay, so runner again. There are two shapes. First is trapezoidal runners or cylindrical runners. Mostly we use cylindrical runners because in trapezoidal runner there is a surface area, large surface area, so you have more heat losses, which is not desirable. So usually we study, or this is cylindrical is most practically used. Okay. Then there are different types of gates. So gate is a basically orifice or a cross-sectional area from which liquid metal actually enters your mold cavity. Okay, so that is called as gate. So there are four types of gates. First is called as vertical or top gate. Then you have bottom gate. Then you have parting line gate. And then you have step gate. Okay. So then there is a derivation for filling time. You should remember how we did the derivation. You can remember for the top two, because if you remember for vertical and bottom, parting line is just combination of both of them. Okay. So there are certain advantages and disadvantages of these gates. So in what, for what kind of material do you use which kind of gating system? It depends on their tendency of oxides, whether the oxides are heavy or light. Okay, so based on that decision, you decide what type of gating assembly is suitable for you. Okay, and then we solved some examples, that that is based on this filling time for top and bottom kind of gating systems. Okay, so go and revise those, because they have been also asked in the gate exam previously, so you should know how to solve this. This step gate is basically, it's used for larger cavities or larger mold cavities, and basically instead of having a single gate, you have multiple gates, so that filling time is reduced, and you'll have uniform properties as much as you can. Okay, so this was about gates. This filling time formula, very important. You should go back and revise those. Okay, we had done some problems also, so it's not the new thing, but very important. Just a hint. Okay. Then we studied something called as unpressurized, pressurized versus pressurized gating systems. Okay. Then there is something called as gating ratio. So for these, unpressurized, you'll have gating ratio of something like 1:2:3, something like that. And for pressurized, you'll have gating ratio of ulta, maybe 2:3:1 or something like that. Basically, choke area, these are defined by choke area. Choke area is nothing but the smallest cross-sectional area in your whole gating system. So if it is if the gate is the choke, then it is pressurized. If your sprue end is the choke, then it is unpressurized. Okay, so all those things we had done. Okay. Then very important topic, which is called as riser characteristics. Okay, another favorite topic for numericals. Okay. So as I said, riser is a very important component of the gating system, because it ensures or it indicates the complete filling of the mold. Okay, and also it supplies, because of the shrinkage from liquid to metal solidification process, additional metal is required, so that the mold cavity is always completely filled. That is also done by riser. So it is not only for completion indication, it serves as a reservoir also of liquid metal for castings. Okay, so therefore you should always remember that riser must after the casting. Okay, so that is the primary objective or the primary rule with which risers are designed. So that means solidification time for riser should be greater than solidification time for casting. Okay. So that means if you had paid attention to our Chauvinov's rule, so this V by A for riser should be greater than V by A for casting. Okay. And then, sometimes in some books or in any questions, in some exam questions, they just reverse this and use this kind of formula. It's all the same thing. Okay. So if you know the logic behind this, you'll be fine. Okay. So then in riser, ideal shape of a riser should be the one which has lowest surface area for given volume, and that is sphere. Okay, but practically this cannot be used because what happens when riser is spherical, the solidification starts from the riser boundary towards the center, and therefore it cannot provide the liquid metal to the casting after a point. Okay, so because there will be a solid layer in between the riser and the casting top. Okay, so sphere is never used. Practically it's a cylindrical. Okay, so mostly risers are cylindrical. Then there are two types: side riser and top riser. So as the name suggests, top is like just on the top of your mold cavity. Side is to the side. Okay. So you should remember there is we did this derivation that for optimum this thing, you know, uh, like if you are choosing top or side. So for side riser, h by d equal to 1 is the optimum. So as far as riser dimensions are considered, you should always take h by d equal to 1 for side riser, and for top riser you should take h by d equal to 2. Okay, so these are optimum dimensions for these risers. Very important, you should always remember these numbers. Okay, so this is how it goes. And then this riser design, again, this is the point, or this is the area from where you should expect some numericals. So riser design, it's a two-step process. So we had discussed this and solved some problems also. So you are always encouraged to go back and check. First step is usually this volume of riser should be equal to 3 times the shrinkage allowance. Okay, shrinkage allowance. So this 3 number is like a thumb rule, not a very not a mathematically derived number. It's a thumb rule. Okay, it has been observed that 3 times if you provide, it's good enough. Okay, so then you get some dimensions for riser because you assume this optimum, right, h by d of 1 or 2, depending on what type of riser is there. Then you check. So this is your second step, or intermediate step also you can call this. Check if a by v of riser is less than a by v of casting. Okay, because that's the criteria, right? And there are two outcomes. If this is satisfied, then uh, that is fine. Okay, so you just stop. So whatever dimensions you got in the first step, those are fine. But many a times it happens that usually this is not found. This inequality is not satisfied. So you have to back calculate dimensions of riser, or riser dimension, based on step 2. Okay, so this is how it goes. So it's not like a just set method. You have to do some logical thinking also. Okay, so very important. You can expect some numericals also on this, because professor also has taken some numericals and so did I. So it's important. Then there is something called as Crane's method for riser design. Okay, so you should know something. It is basically it uses the plot between this volume ratio of volume of riser by volume of casting versus freezing ratio. FR is a freezing ratio, which is nothing but A by V of casting by A by V of riser. So sometimes they ask this definition only. What is the definition of freezing ratios? One mark question like that. But these are used for like a simple, complex, not complex shapes. It is used for simple shapes. Then you have this method called as NRL or shape factor method. Okay, so it is like a upgraded version of Keynes method. So basically here you use a plot of VR versus VC against shape factor. Okay, so shape factor is defined as L plus W by T, so length plus width of casting divided by thickness. Again, you can see it is used for simple castings, and then they have this non-linear plot between these two variables, and sometimes for simple casting it works, and finally sometimes it's another method which is called as modulus method. So modulus is defined as M is V by A. So usually your riser should have 20% more modulus than your casting. Okay, so this again 1.2 number is basically 20% extra. So that also is like a empirical observation. Okay, so those kind of things are there. Then apart from that, you should be also considerate about number of risers depending on your casting dimensions and molds, etc. Distance between the risers, there are some standard formula for that. Okay, so based on that you design, because these methods are for single riser dimensions, right? But how many risers do you need, all those things, those are also sometimes important, especially in case of large castings. So there you need to take the help of some thumb rules or empirical relations. Okay. Then we studied something called as chills and paddings. Both of them promote directional solidification. Chills increase the heat transfer rate, whereas paddings decrease the heat transfer rate. Okay, so you should know the difference between those. And then, towards the last class of casting process, we discussed the various furnaces. Uh, Basically they are categorized as fuel fired and electric. In fuel fired, you have coal, oil, or gas fired. In coal, you have cupola, rotary, and pit furnaces. Whereas in electric, you have arc, induction, resistance furnaces. Okay, so we studied different things. So this cupola is a historic kind of furnace. Nowadays, maybe not that widely used, but historically it was used, and mostly it is used for making cast iron. Okay, producing cast iron. So you should revise what it does. Cast iron has greater than 2% of carbon content. Okay, so you should remember that. If it is less than 2%, it is called as steel. Then you should remember what is the charge for cupola, what is the suitable ratio, what is hot blast cupola, cokeless cupola. There are different zones depending on the temperature. Okay, so I'm not going into those because they're already discussed, but I'm just revising for you what all things you should be careful about. Okay, then in electric arc furnace, obviously the advantage is it is pollution less. I mean, assuming that the electricity that you are using is green electricity, which is not mostly. Then there are certain advantages about electric furnaces. So that's why nowadays they are gaining popularities. And then different types of cast irons we studied: grain, white, malleable, ductile, or nodular. You should remember the keywords about them, okay? Because nodular should have magnesium content. Okay, so we discussed in welding towards the last classes that sometimes when you weld the nodular cast iron, this magnesium tends to uh, become magnesium carbide or magnesium oxide and go away from the uh, material, and that decreases or that changes the cast iron nodular structure. Okay, so all those things are important. Then there is something called as carbon equivalent. Okay, so this came in welding classes also. this something called as carbon equivalent. I'm just again, reminding you that these concepts do not only confine to the metal casting topic; they are used interchangeably in other topics also. Okay, so this carbon equivalent is nothing but whatever you have carbon percentage, whatever silicon percentage you have, divided by 4, plus if you have some phosphorus, divided by 2. So that overall percentage is called as carbon equivalent. Basically, it means if you have 4 silicon atoms in your cast iron or steel, uh, mostly it will be cast iron. That 4 silicon atoms will behave as a single carbon atom as far as hardness is concerned and other effect on other properties are concerned. And phosphorus will become 2 phosphorus will become like a single carbon. Okay, all those things are there. Okay, and this gray cast iron, it doesn't require a riser because, as I said, metal doesn't contract; it expands. Okay, so many a times for gray caster and gray caster in castings, you don't provide risers also. Okay, then there was a discussion on steel, various types of steels: low, mild, medium, high, carbon, ultra high, alloy steels, all those things. Stainless steel, it should have higher chromium content. Okay, and other, like if you want higher hardness, it should have nickel. All those things are there. Then we studied some gas casting defects, gas defects, molding material defects. Okay, like gas defects have blow holes, open holes, scars, blisters, pinhole porosity. Pinhole porosity, keep in mind, because this hydrogen wala defect, right? It is important in all of the processes because of hydrogen. What kind of defects happen? Because they will just mention that pinhole porosity happens due to. Then you should know that it is because of hydrogen getting entrapped in your casting during solidification. Okay, then molding material defects have cuts and washes, drop and dirt, scam, rat tail, swell, buckle, all those things I have given in the notes. Molding metal defects are classified as misrun, cold shut, or slag inclusions. Metallurgical defects, hot tear, hot spots, and all those things are there. Okay. So this was about the revision. But now let's discuss some different types of casting processes. Because sometimes they ask questions on that also. Ideally, we should have discussed this last time only, but I don't know, somehow it skipped. So I'll just give you a brief idea because this information is readily available in many first level books on casting. Okay, so different casting processes. Okay, so they are classified into 3 categories. First is called as expendable molds. Okay, so these are basically expendable or temporary molds. Second is obviously permanent molds. Permanent molds. And last is something called as continuous casting. Okay. So here you have like normal our sand molding. Then you have something called as shell molding. Okay. Then you have something called as investment casting. Then you have full molding. And then you have something called as carbon dioxide molding. Okay, so these are the types of molding or casting processes which fall under expendable kind of molds. So basically you make a mold and you discard it after some time. But here in permanent molds, you usually use metallical molds. So basically like dyes or something, and you don't throw it away because it's used for a mass production. So it is having different subcategories. First is called as centrifugal casting. Then you have something called as die casting. Then you have slush casting. Then you have squeeze casting. Okay. And then third category is called as continuous casting. So basically, as the name suggests, here you continuously keep on producing uh, those things. Okay. So basically, you don't stop in between. So briefly, I'll give you this idea because you know these are, if you just type their name, you'll get to know about them. Okay. So this normal sand molding, everybody knows. You make a mold in the sand, then after a certain number of, or after a casting, you discard that mold. Okay, because it breaks down. Basically, it's a collapsible mold. But this shell casting or shell molding is a tricky thing. Uh, Usually, you use fine dry silica sand, resins, and alcohol. You don't use water here because we operate at temperatures which are around 250 degrees Celsius. So you put that mixture around the particle or the pattern, and then you heat it up to 250 degrees Celsius. Then a shell forms around the pattern, and then you take out that shell, and then you make the mold, okay, out of that shell. So that kind of things are done. The shell molding is used for cylindrical heads, cylindrical blocks, rocker arms. All those things are there. So shell molding, you don't use uh, clay or water. Okay. So uh, mm, yeah, actually, I'll do one thing. I'll just give you some pointers about this because you should remember, because many a times they ask like match the pair, or even from a single method also they will ask something. Shell molding, like high temperatures, 250 to 350 degrees Celsius to make shells. Okay, so you don't use no clay or water. Usually use alcohol and sand only, and you use metallic patterns here because otherwise wood will burn out at 250. Okay, so metallic patterns are used, and resins. So this binding is done by uh, resins, you know, some formaldehyde, basically formaldehydes. So they act as a thermosetting polymers. So you know like that. So advantages of this kind of methods is you just have shell. You don't have the whole uh, mold box to fill, and since this shell is usually harder, so that is one advantage, that once your casting is done, you just have to break this shell off of that casting, and that's easily possible. So, but the thing is, it cannot be used for heavy castings because this shell also have some strength, right? So if it's a very huge casting, you cannot do it by shell casting. Okay, so this is your homework, to refer to any standard book, or even you can do chat GPT also, because since this is a revision class, I'm not able to go into the details of this, but I'm just giving you some things which are like characteristics of these kind of processes, so that if any question is asked, you should be able to answer. Okay. So the thickness of these shells depends on how much time you give. That is called as dwell time, etc. And this shell thickness is proportional to the square root of time, or sometimes it is called as dwell time. Okay, so for how much longer you keep this shell, on metallic pattern, the thicker it will grow. but it's not a linear variation with time. It's a square root variation. Okay. Investment casting, what they do, you know, in investment casting, they will first make the assembly of your patterns. Then they dip that assembly in the slurry of silica flour, ethyl silicate, water, etc., etc., so that your patterns will be completely covered by slurry of ceramic coating. Okay, and these patterns are usually made up of wax. Okay, so wax patterns are used. So first you put slurry on these wax patterns, and then you melt this wax, because wax usually melts at 40-50 degrees Celsius temperature. So then you remove that wax. So you have a hollow shell of ceramic slurry, and then you put liquid metal into it. Okay, so it's like a shell molding only, but it is done for higher temperatures. Okay, so you can go very high temperatures in this kind of castings. The strength will be more because you are using ceramic coating. Okay, so next pattern covered with ceramic coating. Okay, and then wax is removed and all those things are done. So this investment casting, it's like it is used for high temperature applications or high temperature castings, such as gas turbine blades. You can do casting with these. Okay, so now you can see, right, how high temperatures it has to go. Sometimes you can make dentures also using these kind of things, medical implants, etc. So those kind of things are there. So you should just remember what it does. Okay, it is similar to shell casting, but here the temperatures are higher and you use ceramic coating. Okay, you don't use that raising coating. Okay, like in shell casting. Then you have this something called as full molding. So full molding, what you do basically, you know, instead of, okay, one second. Yeah, so this third one is full molding. So this full molding is also called as evaporative pattern casting, EPC, or cavityless molding, or lost foam process. Okay, so these are all the names that are used interchangeably for describing the same process. And as the name suggests, now you can look at these keywords, which is called as evaporative. So what they do basically, they use pattern which is a polystyrene foam or PVC. Okay, so you don't use wood or metal. You use something called as some polymer called as polystyrene foam, PVC, etc. to make the pattern. And then you do normal thing. You don't remove the pattern. You just keep it inside only, and you start pouring the liquid metal. So what happens? This foam, polystyrene, PVC, etc. They will have lower melting points, right? And even like sublimation points or evaporation points are there, boiling points. So liquid metal, when you pour, they just evaporate. Okay, so you don't need to remove the pattern material from the cavity before pouring the liquid metal. Okay, so that is the advantage, that it just evaporates because of higher temperatures. uh, you know Something like that happens. Okay, and sometimes if this plaster of Paris, this is something called as POP, we usually deal with. If POP is used, then this is called as plaster molding. Okay, so the same method, it again has one more name depending on the pattern material. Okay, so you should remember these names: full molding, evaporative pattern casting, cavityless, lost foam, plaster molding, all those things. Okay, so these materials basically have low melting points, and when you pour like molten liquid on these, they just evaporate. Okay, so that is one thing, and you need to have like quite good porosity of your ramming or your mold cavity outside it. Okay, so otherwise it will be having gas defects. And then the last one is something called as CO2 molding. So as the name suggests, CO2 will be involved somewhere in this, correct? So what they do, you have this reaction Na2SiO3, they pass CO2 gas through it, so it will release something called as silica gel and sodium carbonate. Okay, so this is called as a sodium silicate binder. This is sodium silicate binder. Then you have silica gel here. Okay, so basically you make, this is your pattern material now. One second. Yeah, so it's not a pattern material actually. This is added to the sand, to the molding sand. And you have usual patterns like this wood or metal, whatever you want, and then you supply CO2 gas before pouring the metal. So what happens when CO2 gas passes through this sand, molding sand, which has sodium silicate binder. So silica gel will be formed, and silica gel increases the strength of your mold. Okay, so that is why uh, this kind of thing is done. So better bonding properties you will get. Okay, so these kind of things are done. But one disadvantage is that you need CO2 gas, and CO2 gas is not a safe gas for human consumption. Okay, so there is some safety limit, and all those things are there. Then you have permanent molding, right? So permanent molding, first thing, that is centrifugal casting. So as the name suggests, you use centrifugal force during casting. So you will have a uh, you know uh, axisymmetric kind of uh, this mold cavity. You put the liquid metal in it and you start rotating that. Okay, so then it will, because of centrifugal force, depending on how fast or how much omega you give, it will basically give you the thickness depending on that. So basically uh, hollow axisymmetric uh, products can be made out of this. So you basically use centrifugal casting or centrifugal force for casting, and therefore you will have variation in your cast properties in radial direction. Okay, so that is also one disadvantage, that you will not have uniform properties when you do centrifugal casting. Okay, and you know other than that, yeah, I mean, because heat transfer from the outer surface is more than the inner surface, you'll have finer grains, coarser grains towards outside of the casting. Okay, so that's how it goes. And you do, no need of core, no need of cores. Okay, so because centrifugal force itself makes it hollow. But only thing is, it should be axisymmetric and hollow. So that kind of limitations are there. Sometimes it is also called as full centrifugal casting. So basically, it's the same thing. Then you have semi-centrifugal casting. Okay, so this is also part of this centrifugal casting only, but the difference here is you have direction of axis of rotation. Axis of rotation is vertical here. Okay, so here it is axis of rotation is horizontal. Okay, so that's why it is like completely or true centrifugal casting. This is called as semi-centrifugal because you pour from the top to bottom, whereas you rotate in a, so this you can make pulleys, rims, spoked wheels that we use in our bikes or bicycles, etc. So those kind of things are manufactured using this. Okay. So here the limitation is it axisymmetrical is still required, but hollow plus non-hollow be non-hollow also you can make. So that kind of limitation is not this. It can be like solid thing also. Okay. Then there is something called as centrifuging. Okay, so this is also part of centrifugal casting. But here what you do, you basically put 5-6 types of mold cavities at radially different distances, and then you rotate that. So it's you know different centrifugal forces for different molds. Okay, so that kind of things. So these kind of things are there, not that important, but you know you can study those. All of these fall under centrifugal. Okay, then you have something called as die casting. Okay, so die casting, there are two types. First is called as gravity die casting. Second is pressure die casting. Okay, so as the name suggests, gravity die casting, you use, basically you will have a die. So die basically it will be something like this. Okay, so you will make a metallic die like this, and then you'll have uh, some area to pour, and once it solidifies you just remove those dies and you get the final products like this, right? So if you do the solidification under the action of gravity, it is called as uh, gravity die casting. If you deliberately apply external pressure to do faster, or to make sure the liquid metal is in all the places in the mold, then it is a pressure casting. Okay, so those kind of things are there. The advantage is you can use this for mass production, and another advantage is since it's a metallic pattern or metallic die, accuracy and surface finish is high. Okay, so that's why they are uh, used for mass production also. Okay, example could be pistons. In our piston cylinder assembly are made by die casting. And as I said, pressure die casting basically use the pressure to make sure that the fluid or the liquid metal goes into the cavity and solidifies. Okay, so usually it is used for this pressure die casting is usually used for complex shapes, etc. Low melting temperature points, materials, all those things are there. Then then you have another variants of die casting where you supply cooling water also, so that the heat transfer rate or the solidification time can be controlled. All those things are there. Okay, so leave that. Then what are remaining now? Yeah, slush casting and Swiss casting are remaining, right? So yeah, this slush casting is basically you know mm, one second. Yeah, so slush casting is basically similar to this what is it, uh, shell molding. Okay, so the principle is similar to shell molding. Okay, so same here also, you make thin uh, coating, and then you add them. Okay, but the difference here is you use metal. So metal is partially solidified to make shells. Okay, and then from that shells, or here they are called as dies. Okay, so this die is made by partially solidifying liquid metal, and then you pour the other things inside that. Okay, so it's like that only. It's just that instead of polymers, you use metals. Okay, so here also this solidification time is proportional to the square root of thickness. Okay, so one thing, sometimes they ask questions like that. So this is the solidification time for your metal shell or die, and it is usually, nothing is linear in these kind of things. Okay, then last thing is called as squeeze casting. Okay, and this squeeze casting, basically you have a die like this, maybe, let's say. You pour some liquid metal into it, and then you put this plunger. This is called as plunger. This is your die, and this plunger is forced, and then this liquid metal uh, solidifies like that, and then you remove the plunger and you get your final casting. So this is like a forging plus casting kind of combo. So that is called as squeeze casting. Okay. So you know uh, usually these brake shoes and bushes, brass or bronze bushes are used, or casted, like using this method. Okay, and the last one is something called as continuous casting. Okay, so this is like the last category of casting processes. So here you have a huge reservoir of a liquid metal like this. Okay, something like this. Okay, and this is sometimes called as tundish or tundish, however you want to pronounce it. And then you have a die at the bottom of desired length and strength and all those things. Okay, so what happens, this liquid metal uh, will be inside. Okay, one second. Okay. Mm, is this fine? Let's see. No. Anyway, so you'll have some liquid metal like this. Okay, and then, oh sorry, you know, you take it out from the bottom. This flow, you have some rollers so that they rotate in this direction, and you'll have flow in this direction. And usually, they spray some water. Okay, so water sprays are there. This is your dye. Okay, and then this kind of continuous casting process takes place. So as you can see, these long billets or bars can be casted using this, but it is not that easy, you know, because uh, you have to be careful that liquid metal does not come out of the tundish. Okay, so in this case, this control over the cooling rate is very important. Otherwise, it's not that easy to do. Okay, so this is how this continuous casting works. So these are various types of castings that we are supposed to know, casting processes. Okay, so this part was pending because we only had 4 sessions on casting. So I thought today I'll just cover it up so that we have everything done. Okay, so then uh, after casting, we started this metal forming, and first couple of classes we spent on the basics, uh, stress strain kind of things. So you know stresses, there are two types of stresses. One is called as normal stress, another is shear or tangential stress. Both are further divided into direct and indirect or transverse. So direct normal stress, and then there is bending stress. Okay, direct means, I mean, these normal stresses, they will be along the longitudinal axis. Okay, and shear will be perpendicular to the longitudinal axis. Okay, so or for that matter, any axis that you are taking as a reference. So then there are some normal shear, direct normal shear stresses. Oh, yeah. So this is basically shear stress only, but applied in a perpendicular direction to the longitudinal axis, that results in shear stress. And then you have torsion. Okay, so torsion is basically two equal and opposite direction normal stresses are applied at the boundary of the rod or something like that. Okay, then we studied nomenclature for these stresses. This 3D system of sigma xx, sigma yy, sigma zz, then tau xy, all those things. So uh, that was the discussion in our metal forming classes initially. So this stress versus strain. Okay, so these topics we studied. Sign convention is very important. Okay, sign convention, because normal stresses everybody knows, if it is a uh, you know uh, tensile stress, it is positive; it is a compressive stress, it is negative. But sign convention for shear stress is important because it is dependent on the phase and the direction. So if it is a positive direction phase, so phase normal gives the direction of phase. So if it is positive, negative, negative, positive, and the direction of stress is positive, negative, positive, negative. So these four combinations you can have, and the shear stress is positive in first two cases and negative in other two. So what it means is, if you have, let's say, this kind of 2D stress kind of system, and this is your x, or maybe I should draw it somewhere here. Yeah, so this is your x and y directions. So on this face, this face is having positive x direction, so face is positive. And then if you apply shear stress, uh, in the positive y direction like this, then this will be positive, right? So then other things fall into place. Okay, so this is an example of positive shear stress. But in the same case, if you have let's say same example we'll take. So this is your, let's say, x directional phase, positive direction, right? So here if you apply the shear stress in negative direction, so negative y direction, so that means your shear stress will be facing downwards like this on this surface. So then this is a negative shear stress example. Okay, so this is the example of negative shear stress. Very important point, many students forget this, because this kind of things come into picture when you solve some problems. Okay, so then we studied that because of this angular conservation of angular momentum on a small element, this tau xy is equal to tau yx, and tau xz is equal to tau zx. Okay, so these kind of things are there. Then there are three invariants, because there are some properties or some stresses or strain components which do not change based on the orientation of the surface. So they are called as invariants. First one is basically trace of your stress matrix. Second one is nothing but summation of product of normal stresses minus square of shear stresses. Third one is determinant of stress matrix. Okay, so then you have this decomposition of stress matrix into mean or volumetric stress matrix plus deviatoric. So volumetric stress matrix or mean stress matrix is responsible for volume changes, whereas deviatoric is responsible for shear deformation. Then you have 3D strain matrix. Okay, so there basically the difference is that 1/2 factor comes in the shear strain components. Okay, so those things we have seen. Then you have Hooke's law. Hooke's law is valid up to proportional elastic limits. That is the main limiting criteria for Hooke's law, because many times people, I mean, everybody remembers Hooke's law, but they forget where up to what limit it is applicable. It is not applicable up to yield point. It is applicable up to proportional limit, which is lower than the yield point, and we usually assume homogeneous or isotropic material for that. Then Poisson's ratio. It is nothing but lateral strain divided by longitudinal strain. So if you are stretching something, that comes in the denominator, and because of that stretching, since volume is conserved, other two dimensions will contract, so that comes in the numerator, summation of that strain. Okay, so yeah, that was the discussion. And then you have this correlation between different modulus. Okay, so this Young's modulus, shear modulus, and volumetrics, what is it, bulk modulus. Okay, so this E equal to, which is Young's modulus, it is 3k into 1 minus 2 mu is 2g into 1 plus mu. Okay, so this kind of correlations, if you remember, sometimes it is handy. Okay, and mu is basically Poisson's ratio. This is your shear modulus. This is your sorry, bulk modulus. And this is your Young's modulus. Okay. And then we studied the transformation of stress and strain. Mostly stresses are asked in the exams. Strains are usually not. Okay, so uh, this Mohr circle, etc. Those kind of things are important there. Okay, so this Mohr circle, basically, it has the form of circle. Okay, so It is nothing but this sigma xx dash, which is normal stress on the transformed surface, is nothing but sigma xx plus sigma yy. These are your initial normal stresses, plus sigma xx minus sigma yy by 2 into cos 2 theta. So basically this 2 theta is nothing but double the angle of your face from the vertical. Okay, so it will be sine 2 theta. Then you'll have tau xy dash equal to minus sigma xx minus sigma yy by 2 into sine 2 theta plus tau xy into cos 2 theta. Okay, so then basically you can do some simplification, and then you get this equation of circle like this. I am skipping some steps here in between, but not difficult to do. If you just do that, you'll realize how do we get this answer. Okay, so this is your x minus a term plus this is your y square and this is your r square. So this is equation of circle. With center at a comma 0 and radius r. Okay, so the Mohr circle will always have center on x-axis. Okay, which is called as normal stress axis. Okay, and here you can see a is nothing but, which is your center point, that is nothing but sigma xx plus sigma yy by 2, and r, which is the radius of your Mohr circle, is difference by 2 whole square, or this will be r square. So you can just write it that way. Okay. Okay, then there is a sign convention also for this Mohr circle. So from vertical, if you go anti-clockwise theta direction, that is positive 2 theta on Mohr circle rotation, and from vertical if you go clockwise theta, that will be uh, you know, this thing negative 2 theta rotation in your Mohr circle from your starting point. Okay, so that's how it goes. So then once you plot the Mohr circle, other things become easy. Other things, I mean, okay, one second. Yeah, so the thing is, this will be your, let's say, sigma axis, and this is your tau axis. So your principal stress will be sigma 1, sigma 2. So these are your principal stresses, and this will be your tau max and tau min. Okay. So you can just see that tau max is nothing but the radius of your Mohr circle. So tau max is r and tau min is minus r. Sigma 1 is a plus r, sigma 2 is a minus r. Okay, so these things you can just calculate, and depending on your initial condition and all those things, then you rotate. So basically you rotate by 2 theta on this guy. So all those things are there. Okay, so those things are there. We had solved some problems also, and you should remember some key points about the competitive exams, that sometimes they ask the Mohr circle for hydrostatic pressure, so that will be lying on the negative x side point. It will be a point, and radius will be 0. Then in case of pressure vessels, you have higher pressures than the atmosphere, so there it will be a Mohr circle will be a point on positive side of sigma axis. Okay, so those things we had done previously. So you can just revise this 5th week lecture, and then you can solve some problems I think you should be fine. Then we discussed something about this failure theories, etc. Maximum principal stress. Okay, so this is called as Rankine theory. Then maximum principal strain theory, which is called as Saint Vincent or Saint Venant theory. Maximum shear stress theory, which is called as Tresca or J.J. Guest theory. So this first theory, maximum principal stress theory, is good for brittle materials, not for uh, ductile materials. Okay, whereas this Tresca gives conservative measures for ductile materials. It's not good for uh, brittle materials. Tresca is basically, you assume that maximum shear stress is less than the yield shear stress, which is half of your yield stress, tensile yield stress, UTS. Okay, so you should remember the shape of that sigma 1 by sigma, like that, yield locus. Okay, so in case of Rankine theory, it's just a square. In case of Saint Venant theory, it's a rhombus. Tresca theory, it is a hexagon. Okay, so you should remember what kind of what kind of yield locuses are there. Tilted is maximum yield stress, shear stress theory. Maximum strain energy theory, which is also called as Hayes and Beltrami theory. So here basically you compare the strain energy per unit volume, and if it is less than your yield strain energy per volume, then it is a safe design. So it is having yield locus of ellipse. And the last theory is maximum shear strain energy theory or distortion theory or von Mises theory. So it compares yield shear strain energies, not just the strain energy per unit volume. Okay, and you'll also get elliptical shear stress, elliptical yield locus in this case, but that ellipse will be independent of Poisson's ratio. Okay, so just go back and just revisit our 6th week lecture. You'll be knowing these all things. Okay, important to remember what kind of theory is suitable for what type of materials and what kind of yield locuses that you get. Okay, so sometimes they ask about yield locus also. Then in the 7th week, we discussed something about rolling and forging. So, you know, uh, rolling, different types of rolling mills are there, that also we discussed. But, you should understand that in rolling, the material will experience compressive as well as shear stresses. Okay, so it's not purely compression or purely shear, it's combination of both. And then we studied, what happens between the two rolls. So if you zoom in on it, so there will be something called as neutral point, where your velocities will be equal to the roll velocity. But before the neutral point, the velocity of the incoming slab is higher, and because of the supplement of frictional force. And after neutral point, when it goes out, it goes at slower speeds than the roll velocities because of opposite direction of friction. Okay, so those kind of things we studied. And there are some formulas for elongation factor, and very classic example of number of passes required for getting elongation factor of, let's say, 1.2 or something like that. So we have done those. Just go back and check. And then there is a derivation about roll angle, which is also called as contact angle or angle of bite, and projected contact length. Okay, so that roll contact area is nothing but projected contact length into the width of the roll. And then your maximum reduction in height possible per roll is nothing but r into mu square, where r is the radius of roll and mu is the coefficient of friction. Okay, so all those derivations are there in our notes, which are already shared with you. Just go back and study them before your exam. Then you have something called as roll separating force or roll load, which is nothing but there are two formulas for that. But if average flow stress is given, life is easy. But if plane strain yield stress is given, life is slightly difficult, because you have to remember that one formula is there, 2 by root 3 sigma naught bar and all those things. But if it is average flow stress given, which is typically given in most of the gate problems, that is fine. Then you have to use, torque is nothing but roll force or roll load into arm length into omega into 2. 2 because you have two rolls. Omega is basically 2 pi n by 60 roll RPM. Torque is roll load, which we just calculated using average flow stress into BLP, width into projected length. And this arm length, because torque is nothing but force into distance. So that distance is usually taken as 0.5 into LP, projected length, for hot rolling, and 0.45 into LP for this thing, cold rolling. Okay, so that's how you solve those problems. Because many a times they ask you questions in which either you have to calculate maximum height reduction in certain number of passes, or roll power. How much power does you need to provide to the roll in order to get this much reduction or something like that they'll ask. Okay, then we studied forging, some derivations about that, open die forging, closed die forging. Okay, so in forging there are two zones. First is towards the center you'll have sticking zone, towards the periphery you'll have sliding zone. Okay, and then you calculate the total forging force by integrating over those lengths. First of all, you can first calculate what is the boundary. Where is the boundary between your sticking zone and sliding zone? Sometimes you can have the whole length of your forge as sticking zone. That is also possible. It depends on your mu value and h value. Okay, so final height, all those things. So those derivations also we did. You can just go back and revise. And one more question that is typically asked from forging is the sequence of operations. So I've given you two questions in the class only, so you can just check those also, because you cannot have random operations in forging, because as I said, after casting all are derived processes and there will be some sequence of operations. So to get the desired product with desired quality, you have to follow those operations. In case of forging, you have to do fillering first, then edging, then bending, then blocking, then cutting. Okay, so all kind of things are there, so you should always remember those. Okay, then in the last week of our metal forming classes, we studied extrusion process. Extrusion is a peculiar process because it can be used for brittle materials also, along with ductile material also, because there are very few processes which are available for forming of brittle materials. Okay, and extrusion is one of them. So that's one key characteristic you should remember. In extrusion also there are tension plus compression forces, but in many competitive exam questions I have seen that you have to choose only one correct option, and in that case you have to choose compressive stresses, because mostly they are responsible for the plastic deformation at the extrusion die point. Okay, so you have hot extrusion, cold extrusion. Hot extrusion has two types: direct extrusion, in which the direction of die movement is also same as the direction of extrusion product, and in indirect extrusion the directions are reversed. Then in this cold extrusion you have forward extrusion, which is called as hydrostatic extrusion, which is used for brittle materials, and then you have backward extrusion, which is called as impact extrusion, usually used for collapsible tubes used in toothpastes, cosmetics, etc., battery cells, etc. Okay. So this hydrostatic extrusion, which is used for brittle materials, is also called as pressure induced ductility, and all those things are there. Here, as we had elongation factor in rolling, in extrusion you have extrusion ratio, which is A naught by AF. Okay, and sometimes you have this fractional reduction cross sectional area R. So all those things are there. Extrusion force is calculated as K into A naught into ln R. A naught is initial area, K is extrusion constant, and R is this extrusion ratio. Okay, so those formulas are there, we discussed those. Then there are some extrusion defects that you should know. Okay, this bamboo effect, fishtail effect, chevron cracks, all those things. Then in wire drawing, we studied, first of all, there are 4 zones: lubrication, deformation, sizing, and elastic recovery. So you should remember those. And then there is a generalized load equation, which is function of your sigma naught. B is function of your this angle. Okay, so this alpha, what is it called? Diangle. Yeah. So it's a B, so it is diangle. So it is B is equal to mu cot alpha, I think. So that is function of coefficient of friction, as well as uh, this diangle, half semi-diangle basically. And if you have back pressure or back tension, then there is additional term in your load equation. If it is given in the question, take it, otherwise neglect that. Okay, so in ideal case, if you assume frictionless wire drawing, in that case you have to use L'Hospital's rule, and then you get sigma d, which is your mean flow stress, equal to sigma naught into ln a naught by af. Okay, and then there are same problems that how many passes are required for getting desired wire diameter. Okay, so like rolling also, same questions can be framed here also, where it will ask for minimum number of passes or in general number of passes, but in that case they will give you the reduction per pass. Okay, so those examples we have already done, so you can just go back and revise those. Then we studied something called as punching and blanking. So depending on what is your useful part at the end, you call something as punching, and the other thing, if it uh, is blank that is useful, then you call it as blanking. Important stuff in this is something called as penetration factor, because you don't go the full thickness of the material while punching. Once you start the shear deformation, then it will automatically, or without going the full length also, it works. Okay, so that is called as penetration factor. And then there is derivation for minimum diameter of hole that can be punched with given punch. So depending on the punch strength, you can have a limiting diameter for punch. Okay, it is not possible to punch arbitrarily small punch diameter with any punch. That is not possible, because it will be decided by the crushing strength of the punch. Otherwise, your punch will break. No? Then you have drawing operations. Some formulas are there which I have already shared with you. Shallow drawing, where h by d ratio is less than half. Deep drawing, where it is greater than half. And in drawing you have basically bending plus stretching. Okay, so that's why you have bending stresses as well as stretching. I mean, that is like tensile stresses. Okay, and in bending you'll have compression and tensile also. Okay, so all those things are there. In bending, like pure bending operations, there is something called as bending allowance. That also you should remember. It is nothing but theta into r plus kt. So these things usually are given in the problems. Just keep in mind that theta is in radians, okay, not in degree Celsius. And yeah, so this was about forming, and then though we started welding. So welding is quite recent, so I'm not going to do revision for that, because we discussed that quite recently. So, and notes are also shared, and we are at the limit of our time also. So we can revise the welding classes from our notes, because they are very recently done, so no need to revise them. But casting and forming, it has been long time, so better to revise them. In casting also, we had left some important discussion about various types of castings, so that I did today, so that it is whole thing is done now. And yeah, you should go and explore more about these casting processes, maybe from online source or book, whatever is, whichever is you're comfortable with. Main points I have given you, the bullet points. Okay, so this is the end of the final class for this course. And yeah, those who were watching this classes and following the classes, thank you. And hopefully this will help you in maybe for this course exam, or maybe later on if you are preparing for other exams, etc. So with that, I'll stop here. And one last thing, this is not, as I said in the start of this class, this is not the whole production process syllabus. This is just the three part of three main processes out of that. There are many others, so keep that in mind and study that also if required for your exams. Not this course, but maybe later. Okay, so with that I'll stop, and yeah, best of luck for your future endeavors, and hopefully